Hello everyone, I'm Yuzhou from Tsinghua University. I'm going to talk about flow event telemetry on programmable data plan. I finished this work during my internship in Alibaba Cloud. This is the joint work with my colleagues from Alibaba Cloud and Tsinghua University. Today, networks are becoming large and complex. Network applications are more sensitive to network performance and have increasing SLA requirements. On the one hand, the increasing speed remarkably raises the expectation of network performance. Applications like block storage services require higher throughput and lower loss rate. On the other hand, interactive applications have become a major driving force of network business growth, while they also have strong SLA requirements, unstable, and lower latency. If networks can deliver satisfactory performance, we can get guaranteed SLA and great quality of user experience. But bugs and failures in configuration, software, and hardware are inevitable for networks. Thus, applications often suffer from unceasing network performance anomalies. Network performance anomalies can violate SLA. Even occasional latency spikes can bring unacceptable damage to user experience. There are three major types of anomalies, including long-tail latency, bandwidth loss, and packet timeout. According to 2 years application performance problem statistics in production networks, about 46% of anomalies can be attributed to networks. Considering the widespread distribution and the severity of NPA, operators must do cautious and timely NPA mitigation. But the life cycle of NPA mitigation is pretty long and can even last 4 hours. The life cycle has 2 steps. The first one is NPA location, which is about solving a series of problems, including who to blame, what kind of NPA, and where NPA happens. The second one is to fix NPA and recover network performance based on NPA location information. It can be seen that NPA location occupies 90% of the entire mitigation lifecycle. Thus, NPA location is essential to NPA mitigation. For fast NPA location, operators must be able to correlate flows and events. First, the monitoring granularity should be flow level, because precise information about where and how the application traffic gets disturbed can significantly accelerate the cost location. Second, operators should be able to precisely capture all performance-critical events, including congestion, path change, packet pause, and packet drop. Unfortunately, existing network monitors are far from satisfying the requirements for troubleshooting NPA, since they are not designed for capturing flow events. First, traditional switches have black box data planes with weak visibility. They can only export coarse monitoring information. For example, some monitors like syslog provide event-only information, and some monitors like netflow provide flow-only information. Thus, we usually combine coarse information from multiple sources and guess the root cause, which takes a long time even for experienced operators. The overhead of the black box solutions is small, but the coarse data granularity cannot satisfy monitoring flow events. Recently, as data plan becomes more configurable, packet telemetry is proposed for collecting fine-grained data plan information. Packet telemetry can precisely capture flow events. It can extract flow information from packet headers and get event information carried by packet metadata. Although packet telemetry enables fine-grained flow event monitoring, it introduces unacceptable monitoring overheads, since it transmits a lot of monitoring data from data plane to management plane. Existing solutions either compromise scalability or sacrifice granularity. Then, is there an ideal solution that can achieve both fine granularity and cost efficiency? Luckily, recent advances on the commodity programmable data plane have provided us a new foundation for rethinking flow event monitoring. Our key vision is to perform flow event monitoring directly on switch data plane and export exact flow event information. Then, management planes only need to perform simplistic logic over the flow events. We call this new architecture as flow event telemetry, which can achieve both fine granularity and cost efficiency. Thus, we present NetSeer, a flow event telemetry-based network monitor. NetSeer watches all individual flows and comprehensively detects flow events. The key idea of NetSeer is to detect flow events and compress event data entirely inside data planes, so it can significantly reduce the monitoring overhead, as well as preserving the fine granularity. We can change the long-standing situation that NPM mitigation is slow and can take minutes or even hours. With NetSeer, NPM location can be done at real time, which enables second-level NPM mitigation. However, realizing NetSeer is challenging in three aspects. First, it's hard to achieve full event coverage, especially for inter-switch packet jobs. To overcome the coverage challenge, we propose event packet selection. Second, it's hard to achieve high monitoring scalability of event transmission and process. To overcome the scalability challenge, we propose event deduplication, event extraction, and event batching. Last, it's hard to ensure high accuracy within limited ASIC memory. We propose false positive elimination in switch CPU. As shown in the figure, the overall workflow of NetSeer contains 4 steps, and the final bandwidth overhead of NetSeer is as low as 0.01%. For coverage, NetSeer should be able to discover all flow events from high-speed ongoing traffic. There are 4 types of network events: congestion, pause, path change, and packet jobs. Especially, there are 4 types of packet jobs: pipeline job, MMU job, and hardware failure job belong to the inter-switch job. Inter-switch job and the other events are pipeline aware. NetSeer traces the entire packet processing logic in pipeline to comprehensively detect pipeline-aware events. But inter-switch job is pipeline unaware. Although only occupying 18% of job cases, inter-switch job needs long location time. Inter-switch job happens between ports. Due to the reasons like decaying transmitters, packet bits could flip abnormally when a packet is transmitted from upstream port to downstream port. The packet will encounter FCS error and be dropped at switch MAC layer without pipeline visibility. This makes it hard to detect inter-switch packet jobs and recover flow information of dropped packets. NetSeer proposes to leverage inter-switch coordination to detect inter-switch packet jobs. First, for detecting packet jobs, NetSeer will mark each packet with a sequence number. Then, the downstream port will check the sequence number in headers and detect packet jobs when encountering sequence number hole. Second, for recovering flow event information, the downstream port will notify the lost sequence number to the upstream port. Before sending a packet, the upstream port will record flow information and the sequence number of the packet with a RIM buffer. After getting the lost notification, the upstream port can recover the flow event information from the RIM buffer. NetSeer can reduce the monitoring traffic volume by event packet selection. However, extreme situations such as severe congestion can result in massive congested or dropped packets. When networks scale out and the event number grows, the situation can go worse. Imagine a data center with 50,000 servers. Suppose all servers encounter congestion. Then, we need 50,000 processing servers, which brings unacceptable overheads. The key idea to overcome the scalability challenge is to remove monitoring data redundancy without compromising information integrity. First, NiceR removes redundant event packets by event deduplication. Event deduplication compresses event packets into flow events. Next, NiceR removes redundant header and payload by event extraction and batching. In this step, NiceR will generate batches of exact flow events. The state-of-the-art data deduplication method is hashing-based approaches such as Bloom filter. Due to hash collisions, the Bloom filter has an unavoidable possibility of false negatives. False negatives could lead to missing flow events, which cannot satisfy NPA location requirements. To realize false negative-free event deduplication, we design a group caching mechanism. Group caching maintains a hash table. Each entry in the table records an exact file tuple in order to avoid false negative. We hash each event packet to a specific entry. If hash collision happens, the entry is replaced with the file tuple of new packets. Then, both the evicted flow and the new flow will be reported. Group caching enables effective deduplication and zero false negative. To further remove redundancy, NiceR extracts flow event information from raw packets and metadata, and can compress each flow event into 24 bytes. After extraction, flow events are sent to management plane via Ethernet packets. Since an Ethernet packet has at least 64 bytes, sending one event with one packet will lead to large overheads. To address this problem, NiceR proposes to batch flow events, which packs more than one event within each packet, to reduce the bandwidth and processing overhead. The event batching mechanism has an event stack. Each incoming event is pushed into the stack for temporal caching. Meanwhile, NiceR generates circulating event batching packets that constantly recirculate within the pipeline by an internal port. When hitting the stack, the packet pops one event and appends the event into its payload. Once the event number exceeds the threshold, the packet is forwarded to management plane and cloned at the same time with an empty payload to collect later events. NiceR uses group caching table to avoid false negatives, but inevitably, it introduces potential false positives. False positives not only increase data volume to be transmitted, but also mislead network operators, as if multiple independent events have happened to the same flow. However, due to limited programmability and memory, it's hard to fully eliminate false positives on programmable data planes. To overcome the accuracy challenge, we propose to leverage ASIC CPU coordination to achieve zero false positive. First, in switch ASIC, NiceR conducts best effort deduplication, which partially deduplicates redundant event packets and can effectively compress the flow event data with high speed. Then, the flow events with false positives will be further processed by switch CPU, which can leverage massive memory to fully eliminate false positives. We have implemented the board design on Tofino and Smarnic. The implementation has about 12,000 lines of code, and NiceR data is implemented as an extension of switch PIFO. This is the overall implementation of NiceR switch. The inter-switch drop detection modules are at the beginning of ingress and the ending of egress. We lay out the pipeline drop and post detection modules in ingress, enable congestion drop detection in the MMU, and detect congestion, path change, pipeline drop in egress. Flow events from ingress and MMU are redirected to an internal port. All events are processed by the event compression module and finally delivered to the CPU. We have implemented false positive elimination and pacing in switch CPU, and use the reliable TCP to deliver batched events to the backend. Currently, NiceR is under deployment in Alibaba Cloud Networks. NiceR brings moderate data plan resource usage. On SmartNIC, there is 5% additional memory usage. On Tofino, NiceR brings less than 20% resource usage except for stateful LU, and NiceR brings 40% stateful LU resource usage, most for inter-switch job detection and batching. We evaluate NiceR on a testbed with a fat tree topology. The testbed has 32 SmartNICs and 10 Tofino switches. The speed of links between switches is 100 GB per second. We evaluate NiceR in 3 aspects. First, NiceR can effectively accelerate MPA location with over 61% location time reduction. Second, NiceR achieves 100% flow event coverage without false positives. Third, NiceR is highly scalable with 0.01% bandwidth overhead. To understand NiceR's effectiveness on troubleshooting MPA, we study 5 real and representative MPA cases, including congestion, configuration error, routing error, and so on. From our experience of analyzing and debugging the above cases, we observe that existing monitoring systems fail to gather necessary information for MPA location, leading to long location time. Comparatively, NiceR helps operators quickly find related events in seconds. Then, we evaluate NiceR's coverage, accuracy, and scalability on our testbed based on 5 real-world flow traces. First, NiceR can monitor 100% of flow events, and all false positives can be faithfully eliminated. Among the existing monitors, only NiceSight can achieve full event coverage. But NiceSight introduces large monitoring overheads, while NiceR has great scalability with 0.01% bandwidth overhead. So, we have a conclusion. We propose flow event telemetry for fast MPA location. Programmable data plans bring great opportunities for new flow event monitoring algorithms. We design NiceR, a FET-based network monitor that captures flow events with high efficiency. NiceR leverages inter-switch coordination and ASIC CPU coordination to achieve nearly full flow event coverage, good scalability with network sizes, and high accuracy of flow event data. This is the end of my talk. Thanks for listening. We are happy to take any question.